really happy to be here, and thank you for inviting me. So today I'm going to talk about reconstructing training data from the model gradient or the loss gradient. So this is joint work with my student Zihan and Jason over there. Okay. So we know that we have been making a lot of progress of machine learning, and it has been applied to different areas. And we, during our exploration, we are interested in improving the models in different directions. And for the people who know me, previously I worked more on improving the computational and sample efficiency for machine learning. And I would say that is our current, at least efforts in pursuing each directions in machine learning. Most of the time, accuracy or the performance is the top priority. And we also like sample efficiency, what Simon talked about. We want few-shot learning and to be at scale. So in 2 days, there will also be a session about system and machine learning. So people will improve to train models with large scale. And also robustness to adversarial attack, robustness to distributional shift. In any conference or even in this workshop, our attention to exploring different directions is proportional to this shadow here. While the reliable and fairness is also very important part for machine learning, but we have much less attention to that. And today I'm going to talk about privacy, which is a very important part to make machine learning model reliable so that we can really use it in practice. We can trust our machine, safely use it. So to have a reliable model means that we want our model to be robust or not vulnerable to different types of attacks. So what kind of attacks are there? So there is attacks against integrity, which means that it's possible to make the model mislead the model in some specific types of images or samples. And another type is against system availability. So poisonous attack to change or maliciously modify a small portion of training data, but consequently hurt the model performance as a whole. And the last part, which is the focus of today's talk, is attack against privacy and confidentiality. So based on some information we acquire at hand, some adversary will want to infer information about user data. Okay. And in terms of privacy attack, there are also different types. I want to talk a little bit about them so that we understand the relation between them and what is the current progress. So there is a membership inference attack and a reconstruction attack. So these are relatively more popular, or at least exist more in the relevant literature. Well, for membership inference attack, from the name, you can see that they want to infer whether a sample, specific data point, is in the training sample. For example, you have information of a specific client. You want to know if the information of that person has been used in the training data. And reconstruction attack is you have the information about the model gradient or information about the model, and you want to infer or reconstruct what kind of training samples are there. So you can see that a reconstruction attack is actually stronger than membership inference attack, because if you can reconstruct the training data, you will know whether a sample is in the training sample or not. And other types include property inference attacks and model extraction attack, which are relatively less in the literature or in the existing of different types of attacks. And today my focus is reconstruction attacks. Okay, so to describe where the attack or like the vulnerability exists, we can see that it exists in the scenario where like training data, model, and API, the interface, do not like co-locate together. For example, in federated learning, we are talking about soon, the model and training data are not located together. So it is possible that the data set is sensitive, and if people try to like reconstruct data from the model gradient, it will be a problem. So what happens is the adversary can have access to like the interface, and they might want to infer information about the model. Like if you play with ChatGPT or like the model that is not released, but you can play with it. Now, whether you have enough information to reconstruct the model from the queries you have. And another type we are talking about today is like you might have access to the model or might have access to the model gradient, and you want to reconstruct information about the training data. And all the things happens when they are not co-located together. And it will like create some kind of vulnerability. Okay, so let me talk about like the setting we are considering, which is federated learning. So federated learning is an interesting framework proposed by Jacob and Brandon in 2016 and popularized in 2017, etc. And with the like design of federated learning, it is like trying to make give more privacy to our data. So different from our like the training procedure we are more familiar with, we are not like collecting data first and train the model. While in federated learning, all the data are kept in private in the local machine, like the local client. And the data is never transmitted to other client or to the parameter server. Well, what has been exchanged, the information being exchanged is the local update or the gradient computed from the local machines. Well, they exchange the current model and the local update. So a natural question is whether like there exists privacy leakage in distributed learning, especially when the data and model are not co-located. So like the model was like being updated and aggregated by the parameter server, while the data is kept like in private by the local data, by the local client. Okay, so in these settings, since each phone or the local client, they keep their local data, there might exist very sensitive data. Like if I type, like my credit card is something, and we train the model to do the next word prediction, how terrifying if they can reconstruct the samples or the sentence from the model gradient. So our question today is, does local update reveal the training data? Or in other words, is federated learning really like protecting the privacy of our training data? Okay, so interesting, just a few days ago, Professor Kamas has proposed a poll on Twitter, and I guess many of you might have the same question here. So is the following statement true or false? Okay, so federated learning is an effective way to protect the privacy of individual training points. And that was like the, at least the purpose to propose federated learning in the first place. Okay, so apparently a lot of people believe it's true, or at least they said, I don't know, show me. So today I'm going to show you that this is, federated learning is actually not private. Okay, So to talk about the problem, let's look at the formal statement. So the problem is like this. We have local batch of data, so data set written as S. And we have the prediction function that maps from each individual point to the function f. And the information that is being transmitted between the local client and the primary server is the local update, which is the gradient or partial gradient calculated by the batch of training samples. So in a general form, it is written like this. So L is the loss function. The loss function depends on the prediction and the label Y. So our question is, from the information of the local update G, can we reconstruct the training samples S? So the fundamental questions here is, first, is the model gradient G sufficient to identify the training samples? So this is a statistical question. It doesn't involve computation thing. So if we have like infinite computational power, is the information being potentially being reviewed from the model gradient? And the second question is more practical. So if it is sufficient, does there exist like efficient algorithm to actually recover the samples? So these are two questions interacting with each other, but also two separate questions. Okay, so I will talk about some prior work first. There are several attacking methods regarding the reconstruction of the training samples. So they want to learn to generate the training samples from a local user. Some method, they use a generative model to first model the distribution of the data and trying to learn that generative model. So that is a little bit less terrifying. They just want to learn the distribution of the data from a local client, but not like individual data. And another more terrifying thing is with reconstructing individual samples. What they do is to match the gradient, because you see like we have the gradient information. They simply just minimize certain loss, like L2 loss between the gradient and the dummy gradient with the variable xi and yi. So in this setting, the data xi, yi here are dummy variables for the training samples, and they want to match the difference between the actual gradient and the computed ones. Yeah, so the problem is this function is highly non-convex, and in most cases, it's very hard to find the global minimum for this point, even though we know there exists. Okay, and there are this kind of attacking methods. And there also exists certain defending methods, including like quantizing the gradient. For example, they just remove if a certain coordinate in the gradient is small, or like add noise to the gradient. So both methods will like downgrade the performance a little bit, but will potentially help us to improve the privacy. And from the previous empirical work, so I want to emphasize all the previous work are like empirical. They don't have like understanding about whether or indeed we can identify the training samples from the gradient, or they don't know when their method fail, whether it is because statistical problems or their just optimization method failed. Okay, so there are certain beliefs from the previous empirical findings. For example, like at what parameters to query the model gradient. So people believe it is like more efficient to query at moderately trained models, because if they query at initial model or like the random initialization, they think that since the random network hasn't memorized the data or hasn't seen the data it didn't provide much information about the data, so they don't want to query at random initialization. And they also don't want to query at well-trained models, because at that point, the gradient vanishes. Of course, if the model is well-trained, the loss approaches 0 or approach to the station point, then the gradient is almost 0, so there's also little information about the data. So they want to query at moderately trained models. That is from previous empirical findings. And also, previously people also asked whether the gradient alone is enough to identify the images, and previous work believed not. And that is from their empirical findings, because in many cases, if they directly do the gradient matching algorithm, they fail. And they just indicate they think that is because the gradient is not enough to identify the images or identify the samples. And what they do is they introduce some prior information of the training data. For example, they assume the data are from a generative model to reduce the unknowns in their computation. But in this talk, this will be a theoretical work. I will give some negative or counter examples to this belief. And I will say that all these are wrong impressions. Okay. So let me introduce the setting. So as a warm-up, let's look at two-layer neural network first. And all the algorithms, all the results can be extended to higher, to deeper neural networks. Okay. So the prediction function is like this. So W will be the parameters of the first layer, and A is the parameter for the second layer. So as a fully connected function, fx is like the summation of each hidden layer from the first layer and the average of them. Okay, this is two-layer neural network. And our problem is choose to query WJAJ at a proper point, find the gradient, and see if they can help us identify the training samples. And we can see the gradient with respect to AJ is quite simple. It's summation over the loss function, the derivative of each loss function, times sigma. Sigma is the activation function over WJ transpose XJ. Is there any questions to the formulation? Okay, yeah, this is a very common setting for any deep learning theory work. And the difference is previously many people want to learn the weight, learn W or A from the data, but now we want to learn X from the gradient. So sort of like a dual problem. And let's also have some warm-up that you can understand very easily. Let's look at some caveat on the linear and quadratic activations. Let's see if with simple activations, what kind of information we can get from the gradient. And normally, people will think that with linear activation, the problem is simple. Let's get start from linear functions. But in this case, it is much different. And the information we can get with linear activation is very limited. You see, if the activation is linear, if we compute the gradient, the partial gradient with respect to A, the second layer, and the gradient with respect to W, the first layer, the gradient looks like this. It is W times this factor, which is a linear combination of xi. And with the gradient with respect to W, it is also another matrix that is a rank 1 matrix, which is A times the same vector, which is a linear combination of each xi. So this is to say that with this gradient information, At most, what we can learn is this linear combination of the data, but not individual xi. We can only learn a direction that is a linear combination of each data. Well, for the quadratic setting, it is a little bit better, but we can still not learn the training samples. So the gradient with respect to A looks like this, Wj transpose sigma Wj. Well, sigma is like a kind of a second moment with the data, which is the quadratic form of, again, L prime. L is the loss. So the derivative of individual loss times xi transpose. So this means, like with quadratic loss, at most, even if we have a lot of information of W and A, at most we can recover this sigma bar that depends on the data. So we cannot reconstruct individual xi. We can only learn like the span of the data. Just because like the decomposition of matrix are not unique, we can only learn the span of xi, but not individual xi. You agree? Okay. Yeah, but from this, we can also see hope. So if magically we can get information to the third moment of xi, if we can get xi outer product with xi, outer product with xi, which is third order tensor, then we can reconstruct each xi because the tensor decomposition under some mild condition is unique. Okay, so we already say that with linear and quadratic activations, there's no hope. But for other more common activation functions, we can actually reconstruct xi. And that is from a simple and elegant lemma, which is Stein's lemma, or like more generalized version of Stein's lemma. So for a function g, if it depends on W with A transpose W, then expectation of W, well, W generated from a standard Gaussian distribution, if G A transpose W times the Hermite function HW, if we calculate this, this actually is equal to the expectation of the piece derivative of the function G times A to the piece power with outer product. So this is Stein's lemma, but it's a generalized form. For example, the HP is the Hermite function. For example, H2 will equal to WW transpose minus identity matrix. H3 is W to the third power outer product minus W outer product with I and symmetrized it. So basically, it's a nice way to calculate the gradient of any function G with some random samples W. And you will see in a moment how this can help us. Because you see, our function G will be sigma W transpose Xi, where sigma W transpose Xi just comes from the modal gradient. So if we have multiple sigma W transpose Xi, we can query at different W and just make the summation. And with the help of Stein's lemma, this is we can get like the piece derivative of sigma times x to the piece power. So that is used when the order p is, if we can use when the order p is 3, then we get the third order tensor. Well, we will be able to reconstruct xi because this is a nice form of xi to the piece power. So we will be able to approximate this t, where this is like a low rank tensor, where it is of this form, and we can potentially reconstruct each xi from the tensor. So this is sort of like the only math in this algorithm. And if you have any question, I'm happy to stop here and like give you more explanations. So basically, you see G, Wj will be each coordinate of our gradient. And we will do the summation of that and use things lemma to know that the expectation of that will approximate this nice form, which is like a sort of like third moment of xi. And if p is greater or equal to 3, we will be able to reconstruct each xi. Okay, so that means we can like actually query the gradient and at random initialization at like random a standard normal Gaussian W. It will be good for us to get this form of tensor. Okay, remember this GWJ is the gradient with respect to the AJ, which is each coordinate of the second layer, and is of this form. Since this is like roughly sigma over WJ transpose Xi, we can use things lemma with that and get this nice form. Okay. So the main idea, the main next step is, of course, tensor decomposition. If we can, so we show that with the gradient information we have from the federated learning, then we can estimate this TP, which is of this form. And as long as P is greater or equal to 3, we can uniquely identify x1 through xp if they are linearly independent with each other with tensor decomposition. So of course, in general, tensor decomposition is hard, but this is to say that from the gradient information, we are able to identify x1 through xp. I mean, this is a statistical result. If we have like enough computational power, we are able to identify that. So that is to say that we are able to query at random initialization. We can randomly sample AI and WJ to be able to identify the training samples with the gradient. So the previous idea that they think that with random initialization, it is not enough, that is false. Okay. So, of course, there is a problem in the previous analysis, because if, you see, we don't actually have the expectation of this form, but we have like multiple samples, and we want to approximate of this tensor. But if we do a naive approximation, like the number of samples will easily blow up to the dimension to the third power. So, I mean, this M is the number of samples we have, or the dimension of the gradient, or like the number of hidden nodes, or the width of the neural network. So what M is. So if we naively just approximate to this tensor with the gradients, then the dependence of M to the dimension D will be D to the third power. That is very bad, but we have some way to improve that. So this idea actually stems from the previous work, Zhong et al., but they were designing method to optimizing over two-layer neural network, but it is similar to our setting. It is sort of like a dual problem. We can also apply to this problem where we reconstruct X, the training samples from the weight. Okay, so the idea is like we want to first estimate the span of the training data x1 through xp by the second moment, or like use Thanks lemma with p equals to 2, we can reconstruct the matrix. And then, suppose like from the second T2, we get decompose it with V transpose. So here, V will be the same span as the training data. And the second step is like to find T3 operating on V 3 times. Then it will be a much smaller tensor with B times B times B. So B is the batch size. Usually the batch size is very small, for example, 16 or whatever. We can view it at a constant. And we can conduct tensor decomposition of that and get the vectors U1 through UB. And then we project back to the original space. And the idea is, with the second order, to estimate just the span of the training set, that will only require M to scale with D, the linearly with the dimension. So overall, the whole procedure will only like need the width M to scale linearly with the data dimension. Okay, so the conclusion is like this. So the idea applies when the sigma to the third derivative of sigma or the fourth derivative of sigma is not 0. And the reconstruction error, so the L2 difference, the average of L2 distance between our reconstructed x and the true x will be less or equal to square root d over m. So d is the data dimension, m is the number of hidden nodes. So in practice, D will be like a few hundred, and M will be like, for example, 5,000 in like ResNet, etc. And M to be scaling linearly with D is already very good. Okay, and so sigma to the third power or sigma to the fourth power not equal to 0 is very natural, because as we see, with linear or quadratic activations, the problem just fails fundamentally. It is not because of any computational reason, but it's just there's not enough information hidden in the gradient. Okay? Well, here is to say that if like the third derivative of sigma doesn't vanish, for example, it's cubic or it's ReLU sigmoid 10H or liquid ReLU, this is not 0, then it applies. And I also want to mention that even though the previous analysis was on 2-layer neural network, but that naturally extends to like deeper neural networks, because like previous finding is to say we can view this part as the new input. So if the last 2 layers are fully connected, then from our previous analysis, we can reconstruct to the last but 2 layer, the feature from that layer with our analysis. And if we can like design the network so that the previous layers are like bijective, then we can find the input data as well. And actually, this kind of idea was also existing in some previous empirical work. For example, this kind of idea, it doesn't depend on the modality of the data, whether X is image, text, or graph. Well, in some previous work on like sentences, they can first reconstruct embedding and then use some other methods to reconstruct the sentences or like the input data. So this is similar. We can like reconstruct the last but 2 layer first and find some ways to invert the like input images or input samples. Okay. So there are some certain discussions I want to talk about. First, about identifiabilities. Basically, what our conclusion is like, if the expectation of sigma to the third power, sigma to the third derivative, or sigma fourth derivative of sigma is not 0. So, and this works for most activation functions. And also the number of hidden nodes M scales at least linearly with D. So under these two conditions, we will be able to identify the training samples from model gradient at a single query, okay? And another thing is like this is just from our algorithm, but not in general, that deeper neural network does not help or hurt. But potentially, we will hope that when we are dealing with deeper neural networks, we should be able to make use of the information in a better way to get more accurate reconstruction. But our current analysis doesn't help. And I also want to mention that the distinction to linear case or convex optimization. So one evidence is that previously we just mentioned if the activation is linear, which means just when we are dealing with linear prediction functions, then this method doesn't work, or like we cannot identify the individual training samples from model gradient. It is impossible, not just because of our algorithm. So linear models and neural networks are really like fundamentally different in our considered settings of like gradient leakage. And another evidence is in some previous work on like differential privacy, people have like learned that the model is more private at random initialization. As they train the model better, the information being leaked is just increasing. So that is also not the case in the neural network setting. Okay, and some other inspiration on defending algorithm, at least in our algorithm, adding noise to the gradient does not hurt our performance, which means it does not help the privacy. So that will mean that perhaps quantizing the gradient or some other ways to perturb or like encoding the data will potentially be more effective defending algorithms. So these are like some conceptual information we can get from our work. So it was not only just some empirical algorithms to like reconstruct the data, but more importantly is that we have some like theoretical messages from the algorithm, like under what kind of conditions we can identify the training samples from the gradient. And since this is like one of the initial work, the theoretical initial work on understanding reconstructed training samples, of course there are some drawbacks or like disadvantages in our analysis. For example, we only dealt with fully connected neural networks, not like convolutional or like attention layers. In the future, we might want to analyze that as well. And also we haven't done much experiments, and we are working on that. Hopefully we can have good results soon. And I think it is very important to study these directions and especially put more like theoretical efforts into this domain because there was very limited work. And that is the end of this talk. Thank you.
Hi, thank you for the great talk. So I think there was an assumption that the data is linearly independent. Isn't that a strong assumption on real data? Like, could you comment on that? Thank you.
Oh, right. So the data being linearly independent is not a strong assumption. So because you think, so being linear dependent means a certain data is equal to the linear combination of the other data. That is a very weird thing. So in most of cases, so in other words, if you believe the data is generated from a random distribution, then with probability 1, they are linear independent. So it's not a strong assumption at all. Thank you.
I think it's working now. So this was a cool idea, but I think there might be a way to defend against this by using secure aggregation, which is something that people actually do in federated learning. So you may want to look at that.
Yeah, that's a very good point. So yeah, I also want to mention that because like, as I mentioned, that I think the important thing is for us to understand. So for example, we know that adding noise does not help much from the algorithm. Quantizing may be helping. And what you said, we can do many local updates in each client first, and then only transmit the information after that. That will be helpful. So not only is that effective defending algorithm to our algorithm, but to many other like existing gradient matching algorithms as well. Yeah.
So there essentially is a cryptographically secure way to aggregate the gradients, and that's called secure aggregation.
So you mean it's probably secure?
Yeah, in terms of aggregating the gradients. So, but yeah, we can discuss this offline. But I think that that's what secure aggregation provides.
Yeah. Thank you. Yeah, that's a good point. But what's the main message is like when and how does the gradient review or like can identify the information of the training samples. So one gradient can definitely identify that. But if you aggregate it some other secure ways, that will be helpful. Yeah.
Thank you for the talk. Just a question regarding some technical assumptions. So how do you define like the third and fourth derivative for redo, for example? Do you define some generalized derivative of the Dirac mass or something?
I didn't
Okay,
hear.
so there in the identifiability.
Can you move
Okay.
away a little bit from the
Can you hear me now?
Oh, yes.
Okay, so in that assumption,
Which assumption?
like the identifiability.
Oh, yeah. So first line, second line.
Yeah, exactly. First line.
First line.
So you want the expectation of the third derivative and the fourth derivative of the activation
Not
function?
and, or. So
Or
one of them.
One of them, okay?
Is not
How do you find these derivatives for redo, for example? Because you know the first derivative of redo activation function is just the indicator function. Then the second derivative exists in the distribution sense, so it's the Dirac mass.
Yeah.
But for the
You
third,
should think about it in the distributional sense. So like with value is like the third derivative of the expectation of value.
okay, so it's the third derivative of the expectation.
It's like arc cosine something.
Okay. So it's different.
Exists,
it's the derivative of the expectation, not expectation. Okay.
Yeah.
Right. Thank you.
We don't need sigma to be continuous. Yeah.
Yeah. Okay.
Thank you.
Is there a way to design a defense algorithm by revealing a gradient that's imperceptible but changes the higher tensor a lot? Like basically defending by making it hard to do tensor decomposition. Does your work, do you think there's a way to do that, like based on your results? Or like your work has an inspiration for that kind of method?
Oh, so if the data has very, very small norm or like the coordinates with respect to, the component with respect to certain data is very small in the tensor, then it will be harder to reconstruct that. Yeah, that is possible. Yeah.
Hi, I have two questions. Firstly, you mentioned scaling to deep networks. But the way you scale to deep networks is that you go down layer by layer and try to reconstruct a higher layer and then try to reconstruct a lower layer. Doesn't that imply that your error keeps growing exponentially as you go down the layers?
So there's no like noise in the previous layers. So that is different. So
Right,
that
but
depends on like the Lipschitz of the function. So if we are able to query at specific point and we know the model, then we can like just do the reconstruction. There is no noise, so the noise, the error doesn't aggregate.
I see. No, as in the guarantee says that x star minus x recovered is bounded in L2 norm by, let's say, square root d over m. Now, when you do it over multiple layers, doesn't this keep growing as a factor for every layer?
Yeah, for example, let me say in this way. For example, if you consider the first previous layers are value, and you are able to actually reconstruct an identity function. So the error is just exactly the same on the last but 2 layer. It doesn't aggregate. There's no noise in the previous layers.
I see.
Yeah. Thank you for the question.
Sorry, I had one more.
Oh, sure. Go ahead.
In the reconstruction, you needed the expectation over random initializations. How does this scale in practice, in the sense that in the practice you'll only have finite samples from the distribution? Does the reconstruction concentrate very highly on the expectation, or can you comment on?
So that is our analysis. We have analyzed. So there's 2 separate things. First is like there are 2 settings in the attack. So one is like whether we do eavesdropping. So we only observe at certain modal gradient. So in that case, it's like if we have the model at the random initialization, and what people do in practice is normally random Gaussian or random noise, then random weights, then this method works. And another setting is like we can query at a specific point, so we control the parameter server to query at a specific point. So in that case, our method works even better for like a deeper neural network because we can control it. Can you repeat your question again?
Yes. So in the randomly initialized case, at some point you need an expectation to be taken over.
Our analysis shows that if like in the 2 settings, whether we are eavesdropping or we control the parameter server, as long as they are random Gaussian, the weights are random Gaussian, then we only need M to scale linearly with D to have a good reconstruction error.
I see.
So that is the concentration part.
I see. Okay, thank you.
Thank you.